my name is Rachel James. I am a senior at West Virginia University and a 2009 graduate of Lewis County High School located in Weston, West Virginia. I grew up in a little town known as Crawford, West Virginia. It has less than 500 people in the town itself, but I grew up on a farm, so my nearest neighbor is more than a mile away. To this day, we still have well water at my house, no cell phone service, dial-up internet, just middle of nowhere, West Virginia. But I grew up with my mom and my 5 younger brothers. It was a really unique way to grow up. I had a lot of experiences being raised on fresh farm milk and fresh farm eggs, having a garden every year, so I'm really thankful for the way that I was raised. But it made coming to college a big transition. Overnight, I went from having my nearest neighbor being more than a mile away to living with 800 other students in one building. So it was a huge transition for me. I'm first generation, and what that means is that neither of my parents went to college. I'm the first person in my family to go to college. When I came to WVU, I was a business major. I knew that I liked math, but I was a little afraid of science. And so when I decided that business wasn't where I belonged, I decided to go political science. I thought maybe I'd want to get a law degree. And then one evening, a friend of mine that was a mechanical engineering major, he had to attend a department visitation for his freshman engineering course. And I didn't have anything better to do, so I decided to go with him. And the department visitation that we attended was on civil engineering. And I met one of my professors, and he gave a presentation on transportation engineering. And it was just, for lack of a better word, an epiphany. I finally felt like I found where I belonged. I knew exactly what I wanted to do with my life. And I changed my major the next day. So that's kind of how I ended up in engineering. It was almost by accident, so I definitely encourage anyone to take advantage of all the opportunities that you're given. You never know which one's finally going to make everything click for you. Okay, I will graduate with my bachelor's from WVU in civil engineering in May of this year, 2014. From here, I want to attend graduate school. I've recently applied to several universities, including West Virginia, the University of Texas at Austin, and Berkeley, to obtain a master's degree, and I guess we'll see what happens from there. Good morning, everyone. My name is Rachel James. I am a senior at West Virginia University majoring in civil engineering, and I am a 2009 graduate of Lewis County High School in Weston, West Virginia. And today I'm going to introduce you guys to network analysis. So before I begin, here's a little bit about me. As I said, the high school that I attended is located in Weston, West Virginia. I hail from a little town called Crawford. So let me introduce you to where I'm from. As you can see, up here is Morgantown. Weston is about an hour south of Morgantown. If we zoom in a little bit further, here's Weston, and now we're going to focus on this little town here in the bottom called Walkersville. We'll zoom in yet again. The town of Walkersville is over here in this corner, and the farm I grew up on is over here. So I live pretty much in the middle of nowhere. My nearest neighbor was more than a mile away, and it allowed me to have a really interesting childhood. For example, I have 5 younger brothers, and yes, that is a huge black snake that they're holding. And I also had the opportunity to have a pet deer. We had a big storm one summer my freshman year of high school, and when the electric company came to restore our power, they had this fawn in their truck. The mother had been in some down power lines, and so we just kind of adopted her, and she became part of the family. So transitioning to college, I am a first-generation college student. What that means is that neither of my parents attended college. My first semester, I was a business major. My second semester, I was political science. And then finally, the first semester of my sophomore year, I found my way into engineering. So now we'll get into a little bit of network basics. There's a little bit of terminology that you guys need to know before we can proceed. The first is that all of the round circles with the letters in them, those are called nodes. And those are kind of like your locations or your intersections on a map. The two most important are A, which is our origin node. As you can see, the arcs kind of diverge away from A, and they all converge to D. So D is our destination node. Additionally, we need to know arcs, and those are kind of synonymous with our roads themselves. And the numbers associated with all the different arcs are our travel times, or the cost of traversing a network. So here's an introduction to network analysis. We need to find the shortest path from our origin, which is 1, and our destination, which is 4. So there are a few easy steps to finding the shortest path through this deterministic network. First, identify all the possible paths. Go ahead and take a moment to try and identify the 3 possible paths from node 1 to node 4. One option is 1 to 2, 2 to 4. Another option is 1 to 3, 3 to 4. And the third option is 1 to 3, 3 to 2, and 2 to 4. The next step is to sum all the path costs. So by taking 1 to 2 and 2 to 4, we get a total travel cost of 9. By taking 1 to 3 and 3 to 4, we get a total cost of 10. And by taking 1 to 3, 3 to 2, and 2 to 4, we get a total cost of 7. So the last step in finding the shortest path is to select the path with the least cost. And in that case, it's 1 to 3, 3 to 2, and 2 to 4 with a total cost of 7. So now please take a moment and split into groups of 4 to 5. Here's a map of Kingwood, West Virginia. Here's a network analysis problem that we're going to focus on. We're an EMT driver for Preston Memorial Hospital. A 911 call has come in and someone has passed out of the Kingwood Plaza Shopping Center, and we are dispatched. We have to find the shortest path between the hospital and the shopping center to try and save someone's life. So here's our map. The first step is that we have to we have to identify our origin and our destination. The next step is that we have to create a model of the network. As you can see, this is a lot more simple than the map itself, but it will allow us to look at the network more easily. The next thing that we have to do is assign travel costs. Keeping in mind that we need to travel from node 1, which is the hospital, to node 11, which is the shopping center, go ahead and take a moment to try and identify the shortest path. Remember our 3 steps. Identify all the paths through the network, identify the cost of all the paths through the network, and then select the shortest. There are 5 possible paths. So path 1, one of our options is 1 to 5, 5 to 2, 2 to 3, 3 to 8, 8 to 11. Another option is 1 to 5, 5 to 4, 4 to 3, 3 to 8, and 8 to 11. A third option is 1 to 6, 6 to 7, 7 to 4, 4 to 3, 3 to 8, and 8 to 11. The fourth option is 1 to 6, 6 to 9, 9 to 10, 10 to 2, 2 to 3, 3 to 8, and 8 to 11. And the last option is 1 to 6, 6 to 7, 7 to 8, and 8 to 11. So the next step, we have to sum all the path costs. So if we travel from 1 to 5, 5 to 2, 2 to 3, 3 to 8, and 8 to 11, we get a total path cost of 15. If we travel 1 to 5, 5 to 4, 4 to 3, 3 to 8, and 8 to 11, we get a total path cost of 18. By traveling 1 to 6, 6 to 7, 7 to 4, 4 to 3, 3 to 8, and 8 to 11, we get a total path cost of 17. By traveling 1 to 6, 6 to 9, 9 to 10, 10 to 2, 2 to 3, 3 to 8, and 8 to 11, we get a cost of 14. And by traveling 1 to 6, 6 to 7, 7 to 8, and 8 to 11, we get a total cost of 19. So which is our shortest path? Our shortest path is 1 to 6, 6 to 9, 9 to 10, 10 to 2, 2 to 3, 3 to 8, and 8 to 11 with a total cost of 14. So now I'd like to introduce you guys to a little bit of probability. Everyone please grab your Skittles packets. What we're going to do, just bear with me and I promise you'll be allowed to eat them later. But what we're going to do is we're going to open up across the top, make it so that it still maintains its bag, and go ahead and write down which color Skittle you think that you're going to grab without looking at it. I'm going to guess purple, because purple is my favorite color. And I grabbed a red. So as you can see, I was incorrect. How many of you guys managed to guess the correct Skittle? And don't fib, tell me the truth. Look around the room. Not many of you have managed to select the proper color, and that's because you knew absolutely nothing about what was in your Skittles bag. Now, very carefully examine your Skittles to see what the distribution of your Skittles are. I have one Skittle that's stuck inside the bag. So I have 2 greens, 3 yellows, 3 oranges, 2 purples, and 4 reds. So without knowing now that I know what's in my Skittle bag, I know that I am most likely to grab a red Skittle, which is what I did, a yellow Skittle, or an orange Skittle, because those are the ones that occur most commonly. So now I'm going to return my Skittles to my bag. Maybe. Let's do this one by one. And I'm going to kind of try and rearrange them in there so I'm not introducing any bias. And without looking, I'm going to grab another Skittle. I had 4 reds, and red was the most common one. I'm going to guess this time that I'm going to pull out a red Skittle, which I did. How many of you guys were able to guess the correct Skittle this time? As you can see, a lot more of you guys were more successful in selecting the proper Skittle. This can also be done with Starbursts. Without looking, I'm going to guess that I'm going to pull out a red Starburst. And I got an orange. Red wasn't even in my packet. And so now I know that I have 2 Starbursts. One is orange, one is yellow. So if I shake them up in my hand, I have a 50% chance of pulling out an orange and a 50% chance of pulling out a yellow. I can completely eliminate the red and the pink because they're not even in my sample size. So I'm going to guess if they're equal probabilities. Let's go with yellow. Oh, and I was correct. How many of you guys were able to successfully pick out your Starburst that time? So as you can see, knowing a little bit about the probability of something happening makes it a lot more easy to make an educated guess about it. So how do you think that probability is utilized in travel times? Well, are travel times constant, or do they vary? Exactly, they're different. Think about it when you're on a school bus. Does it take you the same amount of time to go to school when it's sunny or when there's snow on the ground? It's going to take you a lot more time when there's snow on the ground because the travel conditions are more hazardous. What about if there's an accident? You have to sit in line, whereas previously if there wasn't an accident, you could go right through. Therefore, civil engineers use the probability of the travel time distributions to make more educated guesses about the accurate travel times. So now we're going to do a little activity incorporating uncertainty into network analysis. You guys may recognize this as the first network that we looked at, where we calculated in the introduction that the shortest path was 1 to 3, 3 to 2, and 2 to 4 with a total cost of 7. Now let's pretend like the link connecting 2 to 3 is on a steep hill. When the weather is bad, the travel time increases to 30 minutes. So let's imagine that there's a 50% chance of heavy snow today. And now as you can see, we have a cost of 3 to travel from 1 to 3, a 50% chance of it taking us 2 minutes, and a 50% chance of it taking us 30 minutes on 3 to 2. And then we know that it's going to take us 2 minutes once we get to 2 to travel to 4. So take a minute and jot down on a piece of paper which route you would pick and why. There's no right answer to this one. We just kind of want to see how you think and why you think the way you do. So this example right here, using the probability distribution of the travel times, is how transportation planners solve such scenarios when there's a lot of uncertainty that we have to incorporate. So why do we care about network analysis? One reason that we care about network analysis is that being able to more accurately predict travel times will help us with congestion mitigation. And I'm going to show you guys a short video on why congestion is such a large problem in larger cities. Another reason that we care about network analysis is the routing of emergency vehicles, just like we did earlier, except for in this case it appears that they're going to a bridge collapse instead of to pick up someone that is passed out. Allowing us to route the most efficiently from one point to another, capturing the uncertainty of travel times, can help save someone's life. Another reason is with the trucking industry. Whenever you have a truck that wants to get to Walmart to be unloaded at 9 o'clock, they don't really care if they can make it there at 7 o'clock if Walmart's not expecting them to get there until 10, because that's when the employees are going to be set down or be waiting to unload the truck. And so with network analysis, we're able to get vehicles to their location as close to the time that they want to be there as possible. And the third example of why we care about network analysis is that it allows us to hypothetically model the spread of diseases through a population. And here's a short video showing you the spread of the flu. So after we figure out the shortest path through a network, the next step for transportation planners is to assign everyone that wants to travel to a route. So there are two types of route assignment problems. The first is all or nothing. So here's a simple example. We have 100 people that are wanting to travel from node 1 to node 2. And we want to figure out how those 100 people are going to be distributed across our network. With all or nothing assignment, everyone will decide to take the shortest path. So the upper link from 1 to 2 has a travel cost of 5. The lower link from 1 to 2 has a travel cost of 7. Therefore, we'll assign 100 people to take the upper link and no one to take the lower link. However, there are a lot of issues with all or nothing traffic assignment. If you put 100 people on a travel network, what's going to happen is there's going to be congestion and their travel time is going to increase until the point that the lower link becomes the shorter travel distance, or the shorter travel time rather. And then everybody's going to want to shift to the lower link because that one's now the fastest. And so one way to combat that is with Wardrop's first principle. With Wardrop's first principle, everyone chooses a route to minimize the total system travel time. What that means is that no one is going to be better off by simultaneously changing their route to the other link. And we do this by solving a system of simultaneous equations, which you should have touched on in Algebra 2. So as you can see, we have an equation that characterizes the upper link, which is 3x plus 10, and an equation that characterizes the lower link, which is 6y plus 4. So we're going to name some variables. We'll say that x is the number of people that are wanting to travel on the upper link, and y is the number of people that are wanting to travel on the lower link. Let's pretend that we have 10 people that are wanting to travel from 1 to 2. So what's one equation that we can make up knowing that we have x number of people that want to travel on the upper link, y number of people that are wanting to travel on the lower link, and 10 total people? Exactly. If we take x plus y, we have to get 10 because that's the total number of people that are wanting to travel in our network. So what happens if we push everybody to the upper link and put no one on the lower link? So x is going to be 10, y is going to be 0. What we get is that we put 10 in for x, so we'll get a total cost of 40. We'll put 0 in for y, and we'll get a total cost of 4. So as soon as people realize that the cost to travel on the upper link is larger than the cost to travel on the lower link, people are going to want to shift their routes. What happens if everyone takes the lower link? We'll set y to equal 10, and we'll set x to equal 0. This is going to give us a cost to travel on the lower link equal to 64, and a cost to travel on the upper link equal to 10. So again, we're going to have that issue of people realizing that the lower link is now slower than the faster link, and they're going to want to shift their paths. So what we need to do is find a way to achieve something known as equilibrium, such that no one is better off by simultaneously changing their route. They're on the quickest path for the entire system. So we do this, like I said, by solving a system of simultaneous equations. We don't want anyone to change their path. Therefore, we need the travel time on the upper link to be equal to the lower link. What equation can we create that will ensure that the cost to travel on the upper link is equal to the cost to travel on the lower link? Exactly. We just set the travel time for path 1 equal to the travel time on path 2, and we get 3x plus 10 equal to 6y plus 4. Now, we have one equation and two unknowns, so we can't solve this problem yet. We need to develop another equation. What other equation do we know about x and y? We know that we have 10, like we said earlier, we know that we have 10 people that are wanting to travel from 1 to 2. X is the total number of people that want to travel on the upper link. Y is the total number of people that want to travel on the lower link. So what equation can we create with this information? So now, how many unknowns do we have? We have 2. We have x and y. How many equations do we have? We have the equation where we set the travel times equal to each other, and the equation where we've linked the total number of people that want to travel. So we have 2 unknowns and 2 equations, and so we can use algebra to solve the problem. So these are the 2 equations that we've created. So now we know that x plus y is equal to 10. We can solve for x or for y in terms of the other variable. And in this case, I've selected to do y is equal to 10 minus x by just subtracting x to the other side. Now what I can do is I can take the other equation and I can plug in this y equal to x minus 10 minus x. I can plug in y is equal to 10 minus x in for y in this equation, and then get one equation with one unknown. And so what this is going to look like is 3x plus 10 is equal to 6 times the quantity of 10 minus x plus 4. From there, I'm able to solve for x by distributing the 6, combining like terms on each side, and getting x by itself. And what I find is that x should equal 6. And when I know that x is equal to 6, I know that the total cost of travel from 1 to 2 is now equal to 28. So now, if x is equal to 6, what's y going to equal to? I know that y is equal to 10 minus x, and so I get y is equal to 10 minus 6, or y is equal to 4. And I'm able to plug y equal to 4 into my travel time equation to find that the total cost to travel on the lower link is also 28. So now I know that on the upper link, x is equal to 6 and the travel time is equal to 28. The time to travel on the lower link is 28 when 4 people want to travel. Therefore, by putting 6 travelers on the upper link and 4 travelers on the lower link, we get a total system travel time of 28 minutes, and no one is better off by simultaneously switching their route, and we have correctly solved the problem. That's the end of my presentation. Your guys' post-activity will be an example very similar to the Wardrop's first principle that we've just solved. So do you guys have any questions that I can answer?